Imagine a universe that stretches endlessly, growing larger every second. Well, you don't need to imagine that. We live in such a universe, but is this infinite expansion really our cosmic destiny? This is what we're going to be discussing today. The universe is approximately 13.8 billion years old. That's right, billion with a B. A number so immense it's practically unfathomable. This age isn't just plucked out of thin air. Oh no, it's the result of meticulous measurements of what we call the cosmic microwave background radiation. This radiation is a relic of the Big Bang, a snapshot of the universe when it was a mere 380,000 years old. It's like the universe's baby photo, if you will. Now let's try to picture the size of the universe. Well, the observable universe, to be precise. The term observable is key here as it refers to the portion of the universe that we can potentially see from Earth, given the limits of the speed of light. This observable universe has a staggering diameter of roughly 93 billion light years. Yes, you heard it right, 93 billion light years. To give you a sense of scale, a light year is the distance light, the fastest thing in the universe, travels in a single year. It's about 9 trillion kilometers, or just over 5.5 trillion miles. But here's the kicker, this observable universe might just be a tiny speck within the actual universe, which could be infinitely large or even one of an infinite number of universes. The mind boggles, doesn't it? This immense universe of ours is not static, though. It's expanding. The galaxies are moving away from us and from each other like dots on an inflating balloon, a concept that's hard to grasp, I know. But it's the reality we live in. So, with this mind-boggling vastness, one might ask, will the universe keep expanding forever? Well, that's the million, or should I say billion, light-year question. And it's what we'll be exploring in the rest of this video. Ever heard of the Hubble Constant? It's not a new brand of coffee, but rather the current expansion rate of the universe. It's a fascinating concept that tells us how fast galaxies are moving away from us. The Hubble constant is pegged at approximately 70 kilometers per second per megaparsec. Now, you might be wondering what a megaparsec is. It's an astronomical unit of distance that's equivalent to roughly 3.26 million light years. So, for every one of these megaparsecs, galaxies are zipping away from us 70 kilometers per second faster. It's like watching the universe play an endless game of hide and seek, with galaxies constantly moving further and further away. And the beauty of it all is that this isn't some slow, leisurely retreat. Oh no, this is a full-on cosmic sprint. And here's the kicker, this expansion might not be slowing down, but rather it's accelerating. What's fueling this acceleration? It's something we call dark energy, and it makes up about 68% of the universe. At this point, you might be wondering what this dark energy is. Well, in simple terms, it's a form of energy that permeates all of space and is believed to be the driver behind the accelerated expansion of the universe. But here's the kicker, we don't exactly know what dark energy is. It's one of the greatest mysteries in modern cosmology. Despite its elusive nature, the effects of dark energy are quite evident in our observations. Remember the Hubble constant that we talked about earlier? Well, it turns out that the universe's expansion isn't just happening at a constant rate. It's actually accelerating, and dark energy is the prime suspect behind this acceleration. The concept of dark energy stems from Albert Einstein's field equations of general relativity. He introduced a term called the cosmological constant to balance out the gravitational pull of matter and keep the universe static. However, when it was later discovered that the universe was actually expanding, this constant was discarded as Einstein's biggest blunder. But with the recent observations of an accelerating universe, the cosmological constant has made a dramatic comeback, this time representing dark energy. A popular explanation for dark energy is the energy of empty space, or the vacuum energy. In quantum mechanics, empty space is not truly empty, but filled with temporary virtual particles that continually form and annihilate. These processes could give rise to an energy density that fills space uniformly, thereby driving the acceleration of the universe. However, this is just one of the many theories out there, and the true nature of dark energy still remains a mystery. But one thing is certain, it's a major player in the cosmic theater, dominating the energy budget of the universe and dictating the fate of its expansion. So, if dark energy continues to do its thing, does that mean our universe could theoretically expand into infinity? It's a mind-boggling thought, isn't it? But that's the beauty of cosmology. It keeps us on our toes, always questioning, always exploring. To answer that, we need to talk about the universe's critical density and the cosmic microwave background radiation. Imagine the universe as a balloon, inflating and expanding. The critical density is the delicate balance point for the universe's expansion. It's the Goldilocks zone of densities, if you will. Not too much, not too little, but just right. This critical density is a minuscule 9.47 times 10 to the power of negative 27 kilograms per cubic meter. Now, if our universe's actual density is more than this critical density, gravity would eventually halt the expansion and cause a collapse. Conversely, if the universe's density is less, it would expand forever. Our current measurements suggest that the universe's actual density is very close to this critical density, which teases us with the tantalizing notion that our universe might just keep on expanding. However, this doesn't paint the whole picture. Let's not forget about the cosmic microwave background radiation, or CMBR. The CMBR is like the universe's baby picture. It gives us a snapshot of the universe when it was just 380,000 years old. This radiation permeates the entire universe and has a temperature of approximately 2.725 Kelvin. It's a remnant from the Big Bang, and its uniformity supports the idea of an isotropic universe, one that looks the same in every direction. The CMBR also gives us a way to measure the universe's density. Variations in the CMBR's temperature allow us to calculate the density of the universe at the time the CMBR was emitted, which, as we've seen, is very close to the critical density. So it seems that the universe's density and the cosmic microwave background radiation are two sides of the same coin, both pointing towards a universe that may keep on expanding. It's like a cosmic dance with density and radiation in step, guiding the universe's continual expansion. With the universe's actual density being very close to this critical density, it's a tantalizing hint that our universe might just keep on expanding. Let's delve a bit deeper into the mysteries of the universe, shall we? Galactic redshifts are a fascinating concept that provides key insights into the rate of universal expansion. You see, as light travels from distant galaxies to us, the universe expands, stretching the light and shifting it towards the red end of the spectrum. This is known as the redshift, and it's directly proportional to the distance of the galaxy from us. The farther a galaxy is, the greater its redshift. This aligns perfectly with the model of an ever-expanding universe. Now, let's shift gears and talk about stars, specifically the oldest known star, which is a mind-boggling 14.5 billion years old. You might think, wait a minute, isn't the universe itself just 13.8 billion years old? And you'd be right. This discrepancy suggests that our understanding of the universe's age might need some fine-tuning. It's a testament to the fact that science is always evolving, always questioning. Next, let's talk about what the universe is made of. Despite what we might think, the stars, galaxies, and everything we can see or touch only make up about 5% of the universe. Yes, you heard that right, just 5%. This is what we call normal matter. The rest of the universe, a whopping 95%, is made up of things we can't see, touch, or fully understand yet. 27% of this is dark matter, a mysterious substance we know very little about. The remaining 68% is dark energy, an even more enigmatic entity that's believed to be driving the acceleration of the universe's expansion. So, with all these numbers and data, the evidence strongly points towards a universe that will keep expanding indefinitely. But remember, in the realm of science, nothing is ever truly settled, and that's what makes it so exciting.